Good morning for all the registrants from Brazil, and good afternoon or evening for those who are abroad. I am Felipe Pedersoli, and I will be the moderator of today's section. Yesterday, I said that we have people from 26 different countries attending our seminar, and as we are in the last day of lectures, I would like to name all these countries and say a big thank you for all the registrants who put effort toward us, even very early in the morning or very late in the night. So here they are. Argentina, Australia, Austria, Belgium, Brazil, Canada, Chile, China, Colombia, El Salvador, Finland, India, Iran, Ireland, Israel, Japan, Mexico, Paraguay, Portugal, South Africa, South Korea, Spain, Sweden, United Kingdom, United States, and Uruguay. And it's impressive because we have the 5 continents represented here with at least one registrant. So a big thank for all of you. It's also important to say that we have many different parts of Brazil being represented here, mainly the states of Minas Gerais, Espírito Santo, São Paulo, Paraná, Rio Grande do Sul, and Pará. So also a big thanks to all the Brazilians that are usually attending our seminar. Once again, I'd like to thank the professors Yara de Muner, Ana Márcia Ladeira, Cláudio Mudado, Rubens Chaves, and my colleague Marcela Cura, who helped to make this seminar possible. It is a pleasure to announce the first speaker of today, Dr. Clarite Azerraf, who will deliver the lecture Cellulose Nanocrystal Production and Applications. Dr. Azerraf has been a part of Melodea since 2013 and currently serves as Melodea's CTO. She has more than 10 years of experience in leading technological developments. Dr. Azerraf holds a PhD in chemistry from the Hebrew University and MBA from Tel Aviv University with specialization in management of technology. She was awarded the Barenholz Award for originality and creativity in practical research by 2010, amongst others. Her specific work resulted in more than a dozen patents and scientific publications. With this very impressive curriculum, I would like to give the floor to Clarite Azerraf and say thank you very much for the collaboration with our event. The speech is all yours, Clarite.
Thank you very much, Felipe. First, I want to say thank you for inviting me for participating in this very important seminar. And I want to say also that I'm very grateful for everyone who's joining. I don't take that as a given. We are all in a very crazy times, and the fact that you stop and taking your time to listen to lectures that you all know that this type of know-how can help us all build a better future, as I hope it's very important. And I hope you enjoy the lecture. And of course, as always, whatever question you have, please feel free to ask in the end. So let's start where we are located. So Melodea is located, as Felipe said, we are an Israeli company. We are in the center of Israel, a little bit south of Tel Aviv. As you may know, Israel is considered the startup nation, and Melodea is definitely a good example of that, because when our company is developing a material that is based on cellulose, while having almost zero pulp and paper industry, this is a very good type of example of how startups in Israel have a lot of courage. So we do have a lot of courage, but we're not that, let's say, stupid enough to think we can do it by ourselves. And we have an amazing investors and strategic partners. First, to invest in the company was Holmen Pulp and Paper from Sweden, and Klabin, who I believe needs no introduction. Our collaboration with these companies and especially with Klabin, I would say, are of course more than strategic. We considered them as friends, and this type of know-how that we have in the collaboration really helped the company during the years to understand what is the market demand, and also navigate us to what we can do in Melodea to answer those demands and the requirements. And as when we are focusing the company as we developed, we focused on two main things. First is the production of CNC. And the second is to develop different products that are based on the CNC. So CNC is cellulose nanocrystals, and I will use the word CNC from now on. But as we will see through the lecture, a little bit background on the material, so you will understand more on, of course, what this material is all about. So the need of renewable materials, green materials, sustainable production, I think needs no introduction. But I think that personally, when I look at the last decade, compare, for example, for what I was taught when I was a student, I was always taught that, yes, green materials are very important. And also it is important that it will be cost effective, but there is a need for green materials. So you can always start, let's say, from some niche market, start developing there, increase your production, the costs will decrease, and therefore you can then go to other markets. Let's say it's a nice thing to learn in the academia, but in reality, not a lot of markets can hold that. Typically what happens is that either only the big companies can afford to wait all that duration until this happens, or that regulation comes and dictates the market, you have to use this or this material. And we as a startup company, of course, cannot afford waiting for that. So the only play that we have is making sure that our material has the best performance that can create a competitive advantage, because for that, companies are willing to pay a higher price. So to understand how this type of green material, which is based on the most abundant material in the world, cellulose, how suddenly it becomes such high performance material, we'll start with short background on the entire nanocellulose family, so you'll have more orientation of what our material is specifically about. Go more, of course, into the detail of CNC, of its properties and its production as well, because it's important to understand the challenges in the production in order to understand how you obtain this type of properties of the material, and for how long can you really have it when you're talking about industrial scale, and start reviewing, okay, now after we produce this great material, what's so great about it? Where can you use it? Naturally, I will focus more on Melodea's activities in terms of the applications, but as you can see, it's quite a lot, so let's start. So I don't think I need to explain why cellulose is an amazing material. But if we look more specifically on why it's a great material, because it gives the strength of every living plant, the truth is that what really gives the strength is the crystalline areas inside the cellulose. So to whoever is not really familiar with the material, so cellulose is built from repeating glucose units, and you have the amorphous areas and the crystalline areas. So when we're discussing the family of nanocellulose, it's all about when you extract parts of the cellulose, the more crystalline areas, are you extracting only crystals or a more long parts of the cellulose? So the longer you get, aiming to a micro size fibers, the less high properties you get, because you naturally also have amorphous areas and not just the crystalline ones. So the first material, MFC, is mainly produced through different techniques of grinding. It is a simple production, relatively, compared to the other materials in the family. Therefore, it also has the lowest cost. It's a cotton candy shaped like fibers, as you can see in the image. But of course, the more long fibers you have, the less ability the material has to have different properties that are different than what you would expect from just cellulose that is grinded. Therefore, it is mainly used as either a rheology modifier or reinforcement, mainly of cellulosic materials such as paper or fibers. As we move along, you can have the CNF, which now this material is already nanoscale in its width. So it still has the length the same as the MFC, but now in width, you're already in the nano size. It gives it, of course, more ability of different assemblies than the MFC, but still it is limited because it's long fibers and it is mainly used in very similar applications such as the MFC. In its how it looks, it is more gel-like, so it actually looks more as the CNC that we will discuss in a second. But it always has the question of why to use a material that costs 100 times more than the MFC. In fact, it is a material that is typically used in Japan. You have there more than 27 companies that deal with this material. It's more historically where it started. And it is mainly also because there is a lot of governmental support for this material. So this is why you will see it mainly in Japan. The CNC has a nano dimension both in length and in width. Because now you can see the road shape like particles, they have the ability of self-assembly. And that self-assembly is the main reason where you get all other properties that you have. It has now the ability to create 2-dimension, 3-dimension structures, as we will see. And now when you open this whole world of opportunities, you get a lot more than just reinforcement or rheology. You can get optical properties and electrical and conductivity and a lot of other properties that now makes the material a lot more attractive for various applications, and let's say not more straightforward as reinforcement of cement or paper or in cosmetics or more simple things, I would say. So let's say that you're very interested in what I said and you want to become now also a producer. It's not that easy. It's not easy because you need to be part of that value chain in the pulp and paper industry in one way or another. You already have producers in the market, so you need to show what are you doing better than what they are doing. And of course, as you will understand when we'll discuss the production, it's not an easy thing to go from piloting to industrial scale. So you really need to bring the edge of what you're doing in the production, so it will be worth. And in the same time, knowing that when you're doing it and your let's say strategy is to have the license, the technology license, you already have a lot of patents in the market for that, for all the existing producers. So it's not that easy, but I would say that there is definitely a lot more room for more producers, and I truly believe that we will see more as the material will enter the market in various applications. So CNC. We need to remember all the time that we are discussing a material that is, of course, 100% bio-based because it's based on cellulose. But I would say that more than everything, it's a platform. It is not off-the-shelf product. You need to understand the material. You need to understand its properties, because in the same time that it has amazing properties, and when you use it right, you can be amazed at what you can accomplish. It is also a material that if you're using it wrong in your system, it can really create an interference. So you need to understand its properties in order to use it right. And that's also some limitation, I would say, from a producer-only perspective point of view, where you cannot just produce the material and send it away. You need your customers to really understand, or alternatively, what we are doing in Melodea in some applications is creating a prepared formula that will be an off-the-shelf, meaning we're creating a formula that then the customer can take and use it in its own custom way that he's using it other materials today. So let's get into a little bit of the properties. So the dimensions, as I said, it can be, and of course, everything is, it's a whole range of dimensions. Between 5 and 20, the average is more towards the 5, length of 150 up to 400, even 500 in length. The average is around 150, 70. As I said, it has self-assembly, as we will see in the applications themselves, into gel, films, and foams. So each of what I've just said is a whole world of know-how and knowing how to use the material into your advantage. And today I'll give you some ideas of how we are doing that. In the image you see, it's already dispersed form, meaning after we finish the extraction of the material, it's actually more milk-like a material where it's in its aggregate form, and you need to give it energy in order to disperse it to this final gel that you can see in the image. Now, the material is liquid crystals, meaning when we're discussing the material, we're not saying it's dissolved, it's dispersed, because it's still crystals. It's just in water, and they are dispersed, and therefore they're not, you don't have any sedimentation or phase separation. Of course, it depends some on the properties that you, and the charge that you put on the surface of the particles, but generally it has to be a stable gel. Due to the ability of the chiral-nematic form of this characteristic of this liquid crystals, you can see in the image, you have this structure that can create a different order. And if you control this different order by pH, conductivity, and other elements in the production or post-production process, you can actually create different colors and get optical properties, or as you can call it, the iridescence of the final material. Melodea CNC is fully transparent and has no coloring, because this is something that we chose more to go to that, because the optical can serve, of course, a lot of different applications, but it's not the applications that we aim to focus, but it is definitely something that can be done even to our material. So before we go to the production itself, I just want you to have in the back of your mind the complexity. So with your permission, I'll go from the end and go back to start. As we discussed in the beginning, we have the need of green material, which is great, but it has to be cost effective. And to be cost effective, it means that you need to have an industrial production. Without it, you won't be able to decrease the price during the years, and you won't be able to really put your new green material in the market. Industrial production means low accuracy. You need simple analysis, off-the-shelf devices in order to have the production. But we're discussing a nanomaterial, and I'm sure a lot of you are familiar with nanotechnology. Let's say the more common one, such as the particles like titanium oxide or cadmium selenide and all of that. And if you do, you know how complicated it is. And it is not off-the-shelf equipment, and the accuracy is very important. And you need to have a repeatable material in order to really know which material goes to which application. So this is just type of complexity you have when you are doing that transportation from, of course, lab to pilot, and from pilot to industrial. And that is on top of the general challenges that you have when you're going through upscaling of any chemical, as simple as it could be. So the nanotechnology even brings additional complexity to that. So in the process itself, we can start in Melodea from different cellulosic material. We have worked with cotton, hemp, flax. Even one of our first patents was actually on the sludge of paper mills. But in reality, we can even, or it is more useful to use a clean either dissolving pulp or bleached softwood, hardwood, it doesn't matter, because that material has the highest alpha cellulose content, and therefore your yield is going to be the highest. But we can also use other materials if needed. We are cleaning them before from whatever is needed, hemicellulose or lignin. But again, there is no reason that we will do some pre-treatment where the industry has done it much better and much efficient than what we can do during the years. So taking a material such as the bleached pulp is fine. It has a cost, but it's of course, if you're putting your plant inside a paper mill, that cost is very low. So we start from looking at what the process is all about. So this is the stages that we have. It starts from hydrolysis. The main known or used hydrolysis is sulfuric acid. There is also a possibility to use hydrochloric acid, but it's less typical due to two main reasons. One is the fact that, of course, sulfuric acid, it doesn't have fumes compared to the HCl, which will make the entire factory more problematic. That's the first thing. The second, you always have in the end residues of acid, and if those residues going to be with chloride residues, it's going to limit you with which type of application in the end you can apply the CNCs. For example, for food applications, you won't be able to. So the typical procedure that you can find in any review is sulfuric acid. It is typically used between 58 to 64, 65% acid. The conditions of the temperature and the ratio between the pulp and the acid, the time, it's very narrow. In reviews, you can find all those ranges, and I can tell all producers are working in those ranges. But again, to know which exact parameter you want to use in order to get a specific final product, that is the know-how. The chemistry here is quite simple. What is not is the rest of the stages. After you do the hydrolysis, then you abstract the crystal and therefore the amorphous cellulose and other carbohydrates that are developed during the process, transformed more correctly during the process, are going to the acid, and you recover we call it pellet. This is your product, and then you start washing it from the excess of acid that you have. After you wash it as far as you can from the acid, you neutralize it, typically with sodium hydroxide, but you can also use other. What you are neutralizing, I'll just explain more correctly, is that not only the a little bit free acid that remains in the solution, but also sulfate groups that now are charged on the surface of the CNC. So you are neutralizing those, and in the end of the process, where, just a second, I'll put the laser so you can see where I'm pointing. So in the end here, where you're finalizing and you're neutralizing material, this is the milky suspension that I've mentioned. And now you need to give it energy. It can be either high pressure homogenizer or some ultrasonic energy to get the final dispersion of the gel-like. Which concentration you can reach, that depends a lot of how much you've charged and the entire process that you created here, and how much you've washed the acid, because any residues of acids or salts, the CNC is very sensitive for that and can create gelation that is on top of the inherent properties of the CNC. Melodea's benchmark CNC is typically 3%, and this is what we market. But the most important thing, if we're discussing specifically now the production of Melodea's CNC, is the acid recovery. And we'll go through that in a second. Just here, when you're looking at this diagram, just to explain where this acid comes from. So After you did the hydrolysis, you recovered your product, but the rest is just acid that is now going to waste, and the acid contains a lot of different carbohydrates, furfuras, and all of that. So having a very sustainable process, and of course, eventually also cost effective, you need to deal with these streams. And we'll see in a second how we do that. So Melodea's production site looks like that. So you can choose if you like -20 or +50 as it now in Israel. This is a very nice image, but typically I know Oceansvik only in ice. So less green, more ice, I know it, but it is a very nice place as well, of course. We started actually by having a demo plant in Oceansvik. It was in a collaboration between 4 partners, ourselves, Holman, More Research, and Rice. Now is Rice, and that was SP Processum. And the intention of this plant was first to really learn into the entire production of CNC, which we have and learned a lot, and we established those power meters that we concluded in our next facility, which is now in Israel. And now the plant is in the commissioning stage and is mostly aimed to work by projects. It has the ability there, for example, to work with different cellulosic material and not just from bleached pulp. Melodea's a plant in Israel. Actually, it's very fresh, and I think it's actually the first time that it is publicly announced that we have finished the commissioning. Of course, we still always working on more improvements, but now the facility is definitely ready to produce. So if I convince you right during this lecture, you should place your order in the end. So just to give you some idea of how a blueprint of this facility. So it's a collaboration between us and a company called Luxembourg. It's a chemical company. We are the complete owner of the plant, but we are renting the place inside the facility. So a lot of the elements were already there, such as this reactor, a lot of tanks, of course, infrastructure of electricity, water, pressure, all the typical things that you need for production. And we brought the main units, additional units that are required specifically for a process. So it's actually on going through 3 different floors, and where the main unit room is actually on the bottom floor. This facility has the ability to have dozens of tons annually dry. Just to clarify this type of a term, when we're discussing on production capacity, we're mentioning in the dry amount, but in fact, Melodea does not dry the CNC. As you've seen in the slide of production, slide on CNC in general, you can see also a Cellulose, which is one of our main competitors, a Canadian company. They do dry the material. We do not believe it from 2 main reasons. One is the fact that to dry the material, you need to invest energy, and then the customer needs to reinvest energy to disperse. And second, it's never redispersed fully, because when you dry the material, you're actually telling the material, leave the water, be together. So the crystals are telling you, great, we want to be together. So there is no reason now for the particles to really separate back. So we always, in the end of the process, leave it in the water form, and disperse or undispersed depends on how we're shipping it. So going back to the acid recovery, which makes this entire process for Melodea cost effective, especially in Israel. It's important to remember that now when we're doing it in Israel, it's kind of it's brownfield operation. It's not green because we're doing it in a chemical factory, but it's not fully integrated in where it is most cost effective, which is pulp mills, because in pulp mills you have the raw material, all the same chemicals, sulfuric acid, sodium hydroxide, and the black liquor is the same liquor that you're using and having in bleach processes. So that will be the most cost effective. So in Israel, if you have waste streams, you pay a lot for them, as you should if you create them. So one of the most important thing that we did in the beginning was to develop an acid recovery process, in which we recover the acid, the used acid that contains 50% of the raw cellulosic material. If I haven't mentioned, the theoretic for a pulp amount of CNC that you have is up to 50, meaning the amount of crystals that you have in alpha cellulose that you have in pulp, 50% will be crystal, 50 is amorphous. So the maximum yield that you can reach in a process is 50, where the other 50 goes into the used acid. And now you have a used acid, which you need to recover it to start over. You can see now here, it's a nice image that shows you where we start from. Of course, it can be a little bit, it depends on how long it's been since the last time that you used it. So even up to 2 weeks, of course, it will become more and more black due to the furfuryls, different furfuryls that are created. But for our process, it's quite robust and you can completely clear. It's based on oxidation, and you get a clear acid and then start the process over. It is a patent already technology, also granted in US, Australia, and more. And it is the key for the cost effectiveness of our process. So we need the competitive cost we've discussed a lot, and you see now how we are aiming in Melodea to reach that. You need to have an adjustable process because, as we just started to discuss, you have a road shape like crystals. It has sulfate groups on the surface. Sometimes you neutralize it, sometimes not. You need different concentrations. It's water-based, so it is specific to some systems. If you want it to be in, let's say, organic solvents, you need to do modifications on that, and that is a whole story that we will discuss in the end in a slide, but you need it to be adjustable in order to be also suitable for different various applications. So here is a table from Agenda 2020 Alliance, where it is divided to some low volume applications to high volume. And inside each column, you can actually find something that's, let's say, more straightforward, such as reinforcement of paper, or if using it as paper fillers and cement and cosmetics, paint. Whereas you have some amazing things such as aerospace and installation and organic lead and 3D printing, and it is amazing that one material can do all of that. So maybe one material can do all of that, but one startup company cannot handle all of that as well. So we in Melodea chose, let's say, the main leading applications that we believe that are the most, we will get to the markets quickest with them and has the highest potential in terms of also volume of material. But from now and then, mainly through different EU projects. So through grants, we also collaborate with university and research centers on other applications as well, because you always have to promote even applications that you think that they are very in the R&D stage, because if companies such as ourselves that are producers won't support that, then those applications will always stay in the R&D stage. So it's important to promote those as well. So we will go through all these applications. First, enhancement of a paint. Mainly it started for us as a collaboration with the ICL Specialty Solution, which is a company of an Israeli company called ICL, Israeli Chemicals. the main use of the CNC was as scratch and abrasion resistance and also as a rheology improvement. But I would say that the main advantage here was the scratch and abrasion. CNC, I always say that its greatest advantage, it's not necessarily the material itself and what the property that it gives, more is the fact that it gives an amazing platform for other active ingredients such as micro size materials, pigments, or nano size, of course, materials that are the active ingredients to enhance their performance. As we will see in different applications, sometimes you have applications such as pigments that, yes, you do have micro materials, and if you use the CNC, then it means now that you can either use less of the pigments and get the same performance, or increase performance by now the fact that because of the CNC and the fact that it is now enables the dispersion of those pigments much better, you get higher performance. But sometimes it's even something much more extreme than that. Materials that you cannot disperse because they are powder and you have no ability to disperse them, in coatings and films and foams, and CNC is actually the only way that you can do that. So it starts from something simple as that, then goes to something that is much more complex, as we will see in a second. The main applications that Melodea is focusing on is our barrier product, which is mainly aimed for the packaging world, flexible packaging mainly. What we do is use CNC, which is by itself has a barrier properties, meaning you take the CNC, you can coat it on different types of surfaces. It can be paper, plastic, a bioplastic, and get oxygen barrier properties. The reason for that is the same as self-assembly that we are always erasing back and back, is which you get the particles to align, and therefore they block any entry of oxygen. Now, the issue when you use only CNC is the fact that CNC is sensitive to water. It came from water solution and wants to come back to that as well. So in reality, most of the packaging are used in different humid conditions. Therefore, using CNC by itself as a barrier is not sufficient. You need to protect it somehow, either by some top layer that will protect it, or creating a formula that by itself can hold the same barrier properties, but in humid conditions. And this is exactly what Melodea has done and delivered. So you can see some of the values here. So for oxygen, the oxygen transmission rate, or in short OTR, can be less than 1 in 70%. Of course, it depends on different surfaces, but we can have that on plastic, for example. You can have also an oil and grease barrier. For you that are not familiar at all with the barrier world, then when you are eating some French fries and you see the oil stain from the fries on the other side of the box that you have, then remember that if you're seeing the oil, you're eating the ink that comes from the outside in. It's always a dual way of transport of material. So the idea is that when you coat paperboard, for example, with our formula, you can have print any logo or whatever you'd like on the outside and not worry that now the greasy food will will penetrate to the paper or paperboard, and then the ink will come inside and to your food, and you will eat that as well. So this is for the oil and grease, and most of the flexible packaging world also need water vapor protection. So we bring that as a whole solution as well, Melodea, for solutions that we've developed. But I think the most important thing to understand here is what is the real need when we're discussing this type of formulations. Of course, the immediate one is, or in the end, is to slowly start replacing plastic. It will not replace, plastic trays that have the firm rigidity that you need to have for trays. But in the beginning, you have a lot of flexible packaging that today are aluminum based. And why? A lot of them is traditional use, and some are actually, you do need to have a high barrier. But Melodea is working with all companies that are even tier one to really understand together what is actually necessary from this packaging, and do you need aluminum in those or plastic, or you can definitely go to the paper, have our solution, and have a fully recyclable solution. Again, the reason is because when you have a package where you have aluminum and plastic inside, the package is unrecyclable. And as we all know, it's not only about recyclability, because a lot of people do not even recycle, even if it's just plastic. So the idea is eventually to have a material that you can put back and either have compostability in the end in a home compost process, or in the beginning, just simply recycle it with your paper feed. Okay, so our solution that is based on CNC is very elegant from that perspective, because you're abstracting it, the best part of the wood, and putting it back into the paper and doing it what it knows to do best. So as in our CNC, our formula is also in its in industrial scale. On top of our CNC plant, we have a commissioned formula production facility that has the production capacity of over 100 tons annually. We already produced 5 tons and used those 5 tons to coat globally more than 10 kilometers of paper in different coating techniques. So it's definitely already in the industrial scale, and we're working with amazing collaborations worldwide in order to have a final product that can look, for example, like this. Pouches, you can put granola bars or a detergent powder that today you're using it either in plastic or even aluminum, and still get the same properties. As I mentioned, we can use it not only on paper, you can use it, the entire barrier application also to biopolymers. Generally, this is the place to state that Melodea is actually very active in a lot of the European grants. We have done, I think, more than 8, 9, if I'm not mistaken. This is the YPAC is actually a project that is about to end this month. A great project where the trays that you see here are based on PHA, PHBV. And for the first time, as far as I know, it was able to coat inside the tray with our CNC-based product and get barrier. And this is important because the way that you create trays is you coat a sheet and then you thermoform it. And typically during thermoforming, a lot of barrier materials can be destroyed, and ours didn't. The entire properties remained, and we get a great product. In this specific project, we are mainly focusing the barrier for trays for fresh pasta and meat, and the barrier is, as I said, inside the tray as well as the lid of the tray. And here again is to replace plastic altogether. Another way to look at those coating is if instead of coating a few grammage, few microns, you can have a really self-standing film. It can be even a few hundred microns of thick film. If you're just using CNC without any formulation, you will have a very stiff and brittle film. So typically, in order to have a better properties, you will need to add some other chemical in order to make it a little bit flexible. But the SAM images that you can see to the right can explain to you why this film is so, for me, it's always an amazing product. It's actually holding in your hand transparent paper. This is what it is. The transparency of such film is very important in applications such as printing electronics. You have no deformation in high temperature. It's printable because it's, again, paper, which can also increase the resolution because now you're using only the crystal parts of the paper and less chemicals that you typically have. It's, of course, completely recyclable material and even biodegradable. But again, it is, I would say, more of the R&D stage, and it's typically actually more used in implementing other particles inside those films, such as conductive films. As you can see to your left is a graphene films that you can have, or other carbon nanotubes and other conductive materials. So this is kind of amazing. You have a isolating material, and you're entering inside of it a conductive material and get conductivity in the end. Also, of course, increase tensile and other mechanical properties. One of the applications that we used it in, you can see in the screen here, is for the GreenSense project, again, an EU project, where it is used for the CNC is used also as a film, but also is entered into the conductive ink. So you're printing with an ink with CNC on top of CNC. And the intention is to have a platform for detection of drug delivery. And it's a very cool application. The 3-dimension form that you can use CNC as is in foams. You can have a very high molecular order and control the structure. Typically, it's done by freezing and then solvent exchange of removing the water without collapsing the entire structure. You can see that you can have a white foams that is based only on cellulosic material, but you can also cure it with different materials, for example, for flame retardation and such. One of the projects that we did in the past called BRIMI, and currently one that's called Reinvent, is in collaboration with our Italian partner, Silcart, who took the upscaling of this foam. So in the lab, we did it in A4. They already did it in A3. So you can see in Czech Republic, we did panel prototype of a whole a room that was used, those panels for acoustic and thermal insulation. You can also, of course, use the material to increase the mechanical properties of different fibers. It could be cotton yarn or other. It is more complex, I would say, to that, and it's for you by yourself. It's something that more the partner needs to do, your industrial partner of the yarn itself, because the best way to get properties is actually coated, single fiber, and not just as a whole, dipping a whole yarn inside a solution. So you get a great properties, but it's more difficult to handle. And as I mentioned, all of our applications that I mentioned so far is using our benchmark CNC, which is a water-based suspension. But if you want to use it in other applications where you have solvent, organic solvent, you need to do some modifications on the surface. So this is also something that Melodea is doing. Typically, it's tailored for specific customers and specific project and products. The main challenge here is, in the end, when you're doing modification, you will get some cellulosic material. But the question is, have you dissolved everything and you're getting some dissolved cellulose, or you still have the crystals, but now with different surface groups that you wanted to have on the surface. So that is the main challenge here. You see an example of this type of solution, which is in the methyl ketone. Another 3D structure you can use the typical CNC is to print, have a 3D printing of the material. This was done in Professor Dechusev's lab, and just imagine using this green and material for even in the future for organs, if you would wish. So it develops along the development of the 3D printing itself, but this is definitely also the type of application that you could use. Here is some summary of the main project that I mentioned, but also we have a new one that we just received, the biomat. Will begin soon, and we're, as I mentioned, we're very active in that as well. I see that we don't have a long time, so I'll just mention two more things. At first, we were very honored to receive this year two main awards. First, in the Packaging Europe, in the Fetch Pack, exactly a year ago, and afterwards from the WPO in the World Star competition. We won for our sustainable packaging. And again, the entire panel that are tier one judges, we won with companies such as Procter & Gamble and Henkel and Michelman, all the big companies, Unilever. So for those companies to give us the reinforcement that our technology has a great potential, great results, that was a great thing. And ways to collaborate with Melodea is typically either purchasing our CNC or a formula. We license our technology for production and do joint development agreements on specific projects together with companies that we believe can bring our material into the market. Here I collected a few recommendations for literature. These are some review or a TED Talk of Professor Dechushev that gives you a lot beyond what I've just mentioned. But I would strongly recommend to follow not only those specific articles, but those specific researchers, because they are the top on their field. The entire nanocellulose researchers, we're a family when we were going to the Nanotechnology conference, and it's always like a reunion, and everyone knows each other because you really have to be on top of your field and only deal with this material for long years to understand it and really have the ability to implement it. So with that said, thank you very much, obrigado, and be happy to answer any questions that you have.
Thank you very much, Clarite. It was very elucidative explanations. And we have a lot of questions, actually. And here we have the first one from Claudio Silva, professor from the Federal University of Viçosa.
Yes.
He said, you have mentioned the use of primary sludge to extract CNC. Would it be more difficult to do that compared to bleached pulp?
So this is the thing. As I mentioned, it is, you can do a pre-treatment and start with different raw materials that even contain lignin or hemicellulose. The question, as indeed asked, why to do that? I mean, you can start from bleached pulp or dissolving pulp. It's all a matter of cost. So the answer is, where are you producing? If you're producing, and who is producing? If the producer is a pulp mill, then it has its own pulp that you want to either recover from different parts of the process. And if it's not bleached, then sometimes you would want to start from bleaching. But typically you're right, and it is much worth to have a raw material with the highest alpha cellulose content.
The next one is also from a student from the Federal University of Viçosa, Mikhail. He said, congratulations for the presentation. What are the important parameters in the process of CNC film formation, and how stable are those types of films?
And the CNC foam formation, you said?
Film formation.
Film formation, okay.
Yeah.
So I think now will be a good place to point out that compared to the CNC production itself and coating, which is industrial, film, if we're discussing films that are self-standing, for example, they're more, I would say, in the R&D stage, meaning it's now basically done by casting. So it doesn't have a lot of parameter. You can simply take the material and cast it. But the main way to do it is make sure in advance that you have a formulation, because if you will just use the CNC, and for example, not use some cross-linker and something like that, you will get a very transparent film, but it will be very brittle. And for that, you will also have a lot of difficulties to remove it from whatever slide or petri dish that you put it in. So I would say the formula is the most important thing.
Another question from the Federal University of Viçosa, Júlio Figueiredo, who works in the pulp and paper laboratory of the university. She said, after preparing CNC by acid hydrolysis, and she cited the sulfuric acid, how can I determine the concentration of CNC after dialysis without using freeze drying? She said, congrats for your presentation.
Thank you very much. We actually, as I said, we do not freeze dry. The concentration of the CNC is done by the most simple method, drying the material. I mean, you simply put it moisture or in oven to up to 240 degrees if you wish. And we assume if you've done your process right and cleaned, especially if you mentioned dialysis. So especially if you did dialysis, then it means that whatever solids that you have in your solution now, even if it's now after dialysis only in 0.5%, this is the concentration that you have. I know that she's mentioning this question because, again, dialysis is done for low concentrations of CNC, so it's sometimes very hard to determine. But what we do in the lab in our typical QA is simply do a lot of repeats, 3 or 5, and then make sure that we have the right concentration. With the right moisture analyzer, you can have the accuracy of 0.001, so it's more than enough.
And Julia also sent you a virtual hug, which is very important these times.
It is. Thank you very much. Take it back.
Another question from Claudio Silva. He said, is there any current use of CNC for water or effluent treatment?
Using CNC for cleaning, right? For waste streams. As much as I know, it is more in the pilot stage. We're not handling it that, but again, it is more complex. I would say that it will be developed due to the costs, because in those type of applications, in any types of waste streams applications, you need to put material and it goes with the waste streams. And the accuracy is a problem, and also the recovery of the CNC is also a problem. So it is more of a pilot things that I know that are existing in different universities, but not something industrial yet.
Now a question from Tamires Andrade, also from the Federal University of Viçosa. Hi, Clarite. Are there already methods to promote the functionalization of cellulose nanocrystals, nanofibers? If so, what are the main processes used and the main challenges?
Yeah, so the first thing that you can change the functionality is through the process itself, meaning the time and temperature and ratio of acid and pulp will dictate how much sulfate groups you have on the surface, as well as the length. So, of course, the length of the particles with the sulfate group will create what is the degree of substitute that you've substituted few of the hydroxyl groups with sulfate. So that will give you the main first functionalization. The second, I would say, is during the washing step, how much acid you remove. Because if you haven't removed enough, then you will still have acid that can create different ionic bonds with the sulfate groups, and therefore less with the applications that you want to apply. And third is if you're going to the extreme, as I said in one of our last slides, is really doing modifications, and that is putting it with different groups all together for different functionality in general. But if you want to still be with the regular water-based CNC and still play with the functionality, it is typically done with different ions and the sulfur groups.
Now we have another question about the drying of CNC from Adriana Pedersoli. She asks you, which chemicals can be added to prevent the hydrogen bonding between nanocellulose in oven drying?
A good question, and not ones that will or everything that you will put will interfere afterwards in the dispersion if you want to redisperse. So the question is, why are you drying? If you're drying only in sense of just to check solid content and such, there is no need for that. The reason to add such chemicals, as she mentioned, is to redisperse them easy later on. But that's the problem. You're adding more chemicals to already complex material, and they're going to be interfering with the CNC ability to interact with other materials, as well as not necessarily you will redisperse the material altogether completely. So we typically do not use it as a permanent thing.
Now I guess we have the last question from Isabella Caroline Diaz. She firstly said, congratulations for your presentation, and asks, which CNC applications cannot be replaced by other nanocellulose such as CNF, and why?
A very good question. The answer is that I think that maybe only nanocellulose producers will even tell you what's the difference between each material in this family. So a lot of time it's actually hard to even detect and say, now the material you have here, this is CNF and this is CNC and this is, so mainly the way that you detect between the difference is the way that you produce. But in the end, once you have produced and it has similar properties, you can use it typically in a lot of similar applications. What will dictate in the end the ability to use one in specific application to other? The simple answer is trial and error. We've tried a lot of different applications. I have to say that originally Melodea did not even want to be a CNC producer. We wanted to develop applications, and we knew that we have producers in the market. They were involving them, but now they already became industrial. But we simply saw that the CNC that we produced, first in lab, then in pilot, now industrial, would the only one who worked. Why? I can give you a lot of educated answers, such as it has this size or this surface charge, but the reality is probably a combination of everything all together. But typically it's the way the material is handled in the end and delivered to you. As long as the material, let's say you've destroyed it during the process as less as possible, then you have a very high quality material and it will perform very well. If you did a lot of other extreme things, such as entering different chemicals during the process, or as the previous question, entering more materials in order to avoid hydrogen bond interaction and such, the material will start to work less and less, and there is the difference. But if you would compare, let's say, inherent material and they were very clean, in a lot of the applications, they will probably work very similar.
Very good, Clarite. As we don't have any other questions, I guess we can quit this first part of the session. Thank you very much once again for attending our invitation. Very clear information, and I guess that all the attendants had a great time with this.
Thank you. It was my pleasure.
Almost an hour and a half of information and knowledge.
Obrigado.
And for those who will attend the next lecture, we will be back in 25 minutes. It's a little bit of time to drink some water, have some breakfast or lunch. I don't know where you are watching us now. And just remember that if you are abroad, we are going to be back at 10 a.m. São Paulo time. And the GMT of Brazil is -3. So pay attention to the time. It's actually in 55 minutes. and we'll be back in the same link, so no need to close it. Just leave it there being broadcast, go to have some lunch, to have some water, and then we'll be back to Mr. Balakshin lecture. Thank you very much, Clarite.
Thank
Hope
you.
to see you again at the Friends of Melody in another event.
Thank you very much. Bye-bye.
Hello again. Now it's time for the second lecture of the day, which will be presented by Mikhail Balakshin. Mikhail Balakshin is an expert in wood chemistry and technology with focus on lignin chemistry and applications. He has strong engineering and R&D technology development background in the pulp and paper industry and biorefinery and significant experience in managing R&D departments and a pilot plant. Professor of Practice in Lignin Chemistry, Aalto University, Finland. To talk about the topic, lignin from fundamentals to application, please, Mr. Balakshin, thank you for accepting the invitation and the speech is all yours.
Okay, thank you very much for inviting me. Thank you for introduction. And bom dia, Brazil, bom dia, Viçosa. Hello, the rest of the world. And let's talk about the most beautiful polymer in the world, it's lignin. And well, Armando Rojas already introduced Aalto University, so I will talk a little bit about our lignin group, which is quite young, a little bit over 2 years. And by the way, you can see 2 Brazilians here in this picture. And what we are, so basically, before we go to topic, from my bio, you can see that I spent half of my career time at university and another half at industry. And also title of my, position is Professor of Practice. So today we will talk not only about fundamental issue of lignin chemistry, but also consider lignin valorization from practical point of view. And talking about main direction in our lignin group at Aalto, so our main topic is lignin engineering. And what we mean lignin engineering, to design specific lignin through understanding correlation between process condition, between lignin structure, between lignin properties, and finally between lignin performance correlation in different applications. And of course, this is a very complex system, and we use artificial intelligence to guide us and to process our data. So we're also working with some biorefinery process like hydrothermal treatment or after hydrolysis, which is green, cost efficient, and we focus this process, well-known process on lignin extraction. Also of our interest in lignin cellulosic synergism in biorefinery streams. Sometimes we need to modify lignin for specific application, and we try to do it through green and cost-efficient ways. And of course, let's say our fundamental is directly related to state-of-the-art comprehensive lignin and lignin carbohydrate complex analysis. So this is a very brief outline of my presentation today. So we will talk about fundamental, and as fundamental, I will try to touch the recent achievement in lignin structure. And then we talk about lignin valorization, and we will consider quite a few issues. First, we have to keep in mind the different market issue when you do lignin valorization. Then we will talk about lignin engineering, and in this topic we will talk about structural analysis of lignin, because again I show that we try to do lignin engineering through process structure performance correlation. So understanding lignin structure is a key point here. And then we see, okay, how we can combine all these elements, process condition, structure, and finally performance correlation. So why do we need lignin chemistry in practical need? Well, understanding structure of lignin is a key point to understand the reactivity of different substrate, either original wood or unbleached pulp, or some other lignocellulosic, to understand reaction mechanism and try to optimize process through reaction mechanism. And also to utilize technical lignin, we have to understand what type of structure do they have. In addition to this, we have to mention that recently there are a lot of variety of lignocellulosic substrate. And this related to different lignocellulosic, like in addition to wood, now we deal with agricultural residue, different waste, etc. Then another raising point right now, especially in Brazil, where you have eucalyptus, there are a lot of breeding programs, both in academia and in industry. It's quite serious. Also, we have to keep in mind genetic engineering of lignin. And then now we have a lot of different technical processes in addition to well-known craft pulp. So what I want to say is that in contrast to different biorefinery products, for example, if you say ethanol, it's, you know, well-defined structure. If you know, say, glucose, it's the same story. Even cellulose chemical structure is quite well-defined. But when we talk about lignin, we use the same words for quite different material. And some people surprise us like, well, why you use exactly the same word for very different substrate? And for me, it's interesting to find this interesting discussion on LinkedIn because some professional answer, okay, well, but you see, if you come to wine store, everything is wine or everything is alcoholic. But you cannot say everything is the same. So you have different variety of red wine, white wine, vodka, spirit, cognac, and so on. So pretty similar story with lignin because it's the same word, but many different material, and sometimes they are very different. And talking about lignin valorization, in our opinion, there is no perfect lignin. Sometimes people try to create lignin and claim, especially small company, oh, our lignin is the best. Well, you know, the situation is quite similar to the paper because depends on where do you want to use your paper, either on tissue or packaging or printing. Then optimum paper type will be quite different. So the same with lignin. So best lignin candidate will depend on application of the looking for. And now we are talking about very basic information about lignin chemistry. So first, how we start. So you can see that generates these three different, what we call lignin precursors. And the difference between them, it's only amount of methoxy group in ortho position to phenolic. So if none, it's parafumaryl alcohol produce so-called H unit. Then if you have one methoxy group, then it will be glycol unit. And if you have two, then it will be syringil unit. And we can see here also nomenclature because with number, usually we code different position on aromatic ring. And with alpha, beta, and gamma, it's not always, but quite traditionally, it's position in side chain. So we see that lignin monomeric unit, they're phenolic, certain amount of methoxy group or none, and also 3 carbon in side chain. But okay, this is not real lignin, this is lignin precursor. And then how lignin polymerize? It's quite simplified scheme here. So first we produce phenolic radical through specific time of enzyme in cell wall. And so this phenolic radical, because you see in coniferous alcohol, it has the different electronic density on different position of C9 unit. And then depends how this radical then couple. So we can have different type of already lignin dimer. So if it's at beta position, so we have so-called beta-beta structure. If you see coupling between oxygen radical and beta position, so it's very common beta-O4 linkages in lignin. And for example, if you have linkages between 5 position of lignin and beta, so then, beta, so then we have beta 5 type, and then it's cyclic, and then we have phenylcumaran structure. And then continue this way, we produce very complex lignin molecules. And here you see like different softwood, hardwood, and non-wood lignin. Very complex structure. And well, again, story is quite similar like to this story about elephant and blind scientist. So you see, elephant is big, so it depends what type of elephant you touch, then you can conclude quite differently about what is elephant. And here's some example. I will just give some example related to lignin. So, okay, well, if you touch aromatic ring, you can say lignin is aromatic. If you touch in the side chain, you can say, well, lignin is aliphatic. Or somebody say lignin is polyol, somebody say lignin is polyphenol. Everything is correct. But what is critical, we have to see not only piece of lignin, we have to see the whole lignin, the whole elephant. And what we can see is very high variety of different structural units and different type of inter-union linkages. And then we have to keep in mind that to see the whole elephant lignin, we have to have a very comprehensive approach for lignin characterization. And now I would like to talk about the structure of very classical softwood, milletwood lignin. And well, we just recently published this critical review where we summarize different analytical data and how this can be translated to lignin structure. And for this specific research, what I will present next slide, I would like to emphasize that here we are talking about milletwood lignin only. This is similar to native lignin, but not exactly native lignin in situ. Because when we isolate, okay, this is the safest way to isolate lignin from biomass right now to get it soluble and be able to characterize, but okay, this is not exactly lignin in situ. So all our data related to milletwood lignin specific. And again, what I mentioned that, well, we have some structural information, then we try to combine this with certain lignin model. And first lignin model was presented by very famous, I would say, grandfather of lignin chemistry, it's Karl Freudenberg in Germany in 1965. And honestly saying, we did not do anything revolutionary since this time. We just, actually lignin development was mostly evolutionary. And you can see from next lignin structure, you can see quite similar to the original one. Again, what is important to understand, in contrast to glucose, in contrast to cellulose, when we draw lignin structure, this is not real lignin structure. This is a model. What means models that we try to visualize certain structural features. But we cannot claim that this is real lignin chemical structure because in most of cases, we can maybe identify some structural motifs, but the critical point, we don't have any even analytical approach to understand how they connected to each other, what are the sequences. So this is like some model show some specific structural element, but some of them closer to real stories, some of them maybe not. So it's important to have in mind that this is model. And well, since Freudenberg, I show some more recent lignin structure. Why I put Sakibara model, which was produced in 1991? Because in my opinion, this is the most quantitative model. What means quantitative? That we have a set of analytical data, and Professor Sakibara tried to construct his model which will fit his analytical data, available analytical data. But this was presented in 1991. And actually for next years, there will be a significant update in understanding of lignin structure, specifically through 2D NMR method. And you see, not long time after Sakibara, Bruno suggests his different model where he put some specific element. But Bruno, Professor Bruno himself, he highlights this model is not quantitative. He just wants to show some structural features there. And I would say the most recent model for native lignin was published by John Ralph in 2090s. And he built his model based on current lignification. So this was his major point. Okay, he used some analytical data, but I will not say very comprehensively. That's why I still refer to quantitative Sakibara model. And if we want to update it, so we have to understand what new came after Sakibara. So this are some key lignin structure. And you see here is current vision and comparing what we have with Sakibara. So okay, we still have major structure as beta-O4 unit. But if you see specific beta-O4, when we have alpha-OH, we have significant difference right now, because this data was obtained by wet chemistry method, which was not very selective. So this is why we have significant difference, specifically in alpha-OH. Then also big difference from Sakibara model, it's amount of beta-beta structure. So you see, now we assume that much less. Then Professor Bruno suggests this 8-ring member structure, what called dibenzodioxazine, this is abbreviation. Also, we realize that, okay, we have this cyclic, but we don't have non-cyclic beta-O4 with alpha-O4, this type. So before it was believed that about 10%, now it's like in a range of 1%, maybe even less. And also much less we have beta-1 structure in current vision. So this is just very briefly to show you, not discussing, because you have this slide you can look later on in terms of functional group and the inter-unit linkages. And then before we go to new model of lignin, I would like to draw your attention on point, okay, what is lignin? Is it linear, branched, or cross-linking polymer? And this is important even for practical need, because, okay, how depends how this affects lignin reactivity. So more cross-linking, usually much more reactive. For lignin application, well, depends on application. Sometimes they want linear, for example, for carbon fiber. Sometimes they want highly cross-linking. Sometimes it's good to have some moderate degree of cross-linking. And by classical version, maybe from 60, from early 70, lignin was always considered like a three-dimensional cross-linking polymer. However, relatively recently, maybe less than 10 years ago, Professor Krishchini suggests, based on her analytical investigation, that lignin, specifically milletwood lignin, and specifically spruce milletwood lignin, is linear. And if you remember, when I show you John Ralph structural model, his model is also quite linear. And it's interesting to discuss why we have two completely different vision on this. And for me, it was very surprising when people did not even discuss it, because people who think lignin is three-dimensional, they ignore this type of claim and vice versa. So it depends whom you trust more. You either say lignin is three-dimensional or very linear. So we decide to reevaluate this. And then, okay, first talking about lignin structure, let's define how many we have terminal units. And you know, since we have side chain and aromatic ring, so we can have terminal unit either in side chain, and this is a different type of this. All of them small, but all together they come like 18%. So in addition to coniferous alcohol, which is only 2% per 100 aromatic unit. So, but then we have some other minor like coniferous aldehyde and other. And in aromatic ring, what will be terminal unit is free phenolic. When we have phenolic and which is not condensing, so it means no linkages in aromatic ring. So if we sum all this data, we will get that the amount of terminal unit in lignin is very high, it's 44%. And then let's try to draw, okay, knowing this number, how we can draw linear polymers. So if our degree of polymerization is 2, so we have terminal and terminal units, so 100%. Then degree of polymerization 2, so we have terminal, internal unit, and again terminal, 67. And then dp4, 5, so we have amount of terminal unit 50 or 40 between. So our it's experimental 44, so we are between. So it means that we can have linear lignin only if degree of polymerization between 4 and 5, average. And by the way, this is very well-known, well-accepted information. It's not only one single method, it's not new, it was confirmed by different independent method, both NMR and wet chemistry, so it's very solid information. And then we look on micro features of millet-wood lignin, and specifically molecular weight. And very recently, our colleague and friends at Boku, like Antipod has Thomas Razino group, they work quite a lot on absolute molecular weight determination of lignin. And when we analyze our millet-wood lignin, we determine that average molecular weight, we're talking about average, because of course we have distribution, we have many different type of lignin molecules and different molecular weight, but we're talking about average. So it's about 4,500. And then it translates us knowing about, so basically degree of polymerization will be about 25 average. Then, okay, so if you try to build lignin molecules, so we will have to have 25 units. And 44% of them will be terminal. It means that 11 units per 25 will be terminal. And then, okay, well, if you have only one chain, it will be only 2 terminal units. Definitely, we are far away from linear. And then we have to understand that each branching unit will introduce 1 extra terminal unit, and each cross-linking will introduce 2 extra terminal units. And then we have this equation. So if we have like sum of branching and cross-linking unit, so in this relation, they should be about 9. So again, from this, not fine chemistry, but very basic micro features of lignin, we see that it's very hard to draw it linear. By the way, it's very interesting plot when we see how degree of branching depends on degree of polymerization. So we can see that, okay, well, what I showed on previous slide, that we will have linear lignin with our DP4, and then it will be more and more branched. And then you see when we go above DP20, then it's not so many change. So basically, after increasing DP more than 20, degree of branching does not change much. And you see we are in this range of 25 and further. So basically, with this degree of polymerization, with this molecular weight, it's very difficult to draw linear lignin for us. So let's consider what kind of branching and the cross-linking point can we have in lignin. So usually it's a so-called 5-5 unit, but depends if they're both phenolic, so it's no branching, it's just we continue chain, so lignin coming here and goes there. But if we have half a terrified 5-5 unit, then we have branching because this is our main chain, and this is already branching point. And the different type of linkages, again, a terrified 4 or 5 unit. So they also branched. And then if you have both a terrified 5-5 unit, so completely terrified, so then they are cross-linked. So let's review the amount in millet-wood lignin through literature data and through our own data. And here we evaluate the amount of branching unit 5-5 and 4-5 by different methods. Well, I will not go to all these details, just please know that we have 5 independent methods, and only one of them, so-called DFIC, phosphorus and NMR, show very low amount of branching unit. All other methods like permanent oxidation, like thiazolidase coupled with phosphorus and NMR, and 2 different quantitative carbon NMR approach give us pretty high amount of mostly 5-5 and small amount of 4-5 units. So you see what is important here, that, okay, why Claudia Coscini decides that lignin is linear, because she uses this method. But she ignored all other methods, which we already published by this time. And you see, if you see that 4 methods show that lignin is pretty branched, and only 1 method shows that lignin has very little branching point. Then from this data, we come back to our potential branching point and say, okay, well, 4 or 5 is very low, below 1%, so we just ignore it. Then we have one structure, again, we're talking about our 25 unit model. So from 25, we have 1 dibenzodioxazine, which is branched. And then we have 2 5-5 terrified, so we have 2 cross-linking points. And again, if you remember this equation, so now we found one branch and two cross-linking, so altogether they give 5, and we have to get 9. So we still about half of branching or cross-linking point are missing. And then we go to material balance in carbon NMR, and through all these details, which were published a long time ago by Evelyn Kapanema in 2004, where we suggest that we have quite significant amount of alpha OOQ or gamma OOQ unit, which are not so seriously considering in lignin chemistry so far. This is quite an unusual point, but at the same time, it was supported some data like from Glasser and Glasser when they do computer modeling in 1974, and also work of Professor Terashima in Japan, and actually he did all around the world with C13 enrichment. He also showed that he has significant amount of this type of linkages in lignin. So then we look further. Okay, well, we look at 2D NMR of millet-wood lignin, specifically SHQC method. And we see that if we have powerful spectrometers, so we can see quite a lot of signal which people ignore, usually. Okay, a lot of people see this spectrum because this is well known, very well investigated millet-wood lignin, but basically people ignore this signal because they think, well, usually it's okay, this is carbohydrate contaminant. But we can see that the amount of carbohydrate in our lignin is very low, less than 1%. So carbohydrate contribute here, but not much. Most of this lignin, most of this signal are lignin. And another interesting feature that you can see is not only one signal, it's number of different signals here and there. And then we suggest that, okay, we could not make this a very clear assignment so far because we don't have enough information. But this signal belongs to this type of structure. We call this tentative because we are quite confident of type. This is OQ or OQ, either here gamma or here alpha. But we don't know exact structure yet. That is why we call this tentative. And then we make material balance of each specific point of lignin, gamma, beta, alpha, and the 4 position of aromatic ring. And we can see that in most of cases, we identified like in beta position almost everything. In alpha, in gamma and alpha, it's about 15% of lignin union non-identified. And from previous data set, we tentatively assign them that gamma OOQ or alpha OOQ. And then knowing all this information, what I showed on previous slide here, we have to build up some kind of lignin structure to draw it. And you see, it's pretty much like a puzzle. But what is a problem with our puzzle? Because quite often we miss certain pieces here. And I think in contrast to most of puzzle, we can make assemble of different units in many different ways. Not many, but quite a few different ways. So this makes quite difficult, but basically we are able to construct this type of lignin. And you can see all details in this paper because we don't have possibility to discuss it all right now. So we comprehensively review not only our own, but all available analytical data. And then we build this model, and this model, of course, this is not the only possible, but at least this model does not contradict neither all available quantitative data, structural data, or absolute molecular mass measurement. And these two measurements were independent of each other. So basically, our theoretical structure fit both requirements. And surprisingly, we were pretty confident that lignin is cross-linked, but we found that lignin is even more cross-linked than we believed before. Not only we, but the whole lignin community. Because we just confirmed that, okay, well, we have significant amount of 5,5 cross-linking point, which was pretty known. We just have to reconfirm it again. But also we found that another half of cross-linking point are located in the side chain and through OQ linkages. Yes, and we have to tell that, okay, for example, here or there, we don't know exact structure. That is why we draw it with kind of dashed line. We are confident of type of linkages, but we don't know exact structure on alpha, beta, gamma position. So that is why we call it like tentative, because it's not exact structure. Then, okay, if you compare back John Ralph model, and this is specifically softwood lignin, you can see that this is very linear lignin molecules versus our very branched and cross-linked. So we really have to state to understand that we have significant conflict between lignification theory, which John used for his model, and between our approach when we use just all set of analytical data. And we already presented like maybe 1 year ago in Japan, and most of criticism was, oh, your model is impossible because it contradicts theory. Well, we do respect theory, this is very nice theory, but when we have conflict between theory and well-defined analytical data, well, I think that we have to modify theory. We should not modify experimental fact. And that's why we suggest that, okay, it does not mean that lignification theory is wrong, but maybe it's not complete and it should be updated, considering some additional biosynthetic routes. Also, we have to understand, I highlight a couple of times, because this is millet-wood lignin, not lignin in situ, and maybe some structural changes here happen when we isolate millet-wood lignin. Not major, but certain minor changes should be considered. And now we go to the second part of our presentation, of our discussion related to valorization of technical lignin. And when we talk about industrial lignin application, you might heard of very notorious old-fashioned joke. You can make anything but money from lignin. And I have to say this is not funny anymore. And by the way, when we work at Reinvent, we did real lignin money, literally. So you can see this coin written Reinvent, pound, and this money made from lignin, literally. But okay, this joke, but so now we have to say, okay, well, this is definitely wrong and definitely not funny. So we have to correct. If you talk about biorefinery must make money from lignin to be commercially successful. And today we are not going to discuss if we can make money from lignin, because answer is obvious and it's already proven like in industrial scale by many companies. So we will discuss what will be the best way to make money from lignin. And if you talk about current biorefinery is sugar-oriented. Main product are sugar or ethanol or something related, and lignin is a waste. I would say it's not often, pretty rare right now. In most cases, it's considered like fuel, or in best case, like low-value feedstock for some aromatic chemicals. And from this point of view, biorefinery is optimized only for sugar. The lignin is just left over. Nobody cares about lignin, and if you want to valorize lignin, you get what you get from biorefinery. But we know that none of biorefinery runs so far on industrial scale. So why? Because significant economical challenges. So we have to change this approach. So, and how we can change lignin? So some people try to make America great again. We try to make biorefinery working. And let's see, consider sugar. How much we can get from sugar, from ton of biomass. It's about this value. Okay, if we use lignin as fuel, we can add to biorefinery revenue with this amount. Not much, but still good, but not much. But if you can make lignin as high-value product for high-value application, then you see we can get similar or even much more revenue for biorefinery. How we can make it? Because we have to produce specific lignin which fit high-value application, and we can do it through different process conditions. So if you play with different process conditions, it will not affect much of. We always get sugar. It's a question like yield, a little bit more, a little bit less sugar, ethanol, but we still can sell because it doesn't affect much of their properties. But for lignin, it's okay. Either we get it for high value and make it working for this revenue, or the only we can get is just burn. So key point that the lignin can be sold for high value only if required characteristics are achieved. And then we come to kind of surprising conclusion, because even if you want to produce bioethanol, but we want our biorefinery economically successful, the process must be focused on lignin engineering to get this value for economical revenue. And we are talking about ethanol, but I guess you heard already quite a few presentations what a beautiful product we can get from biomass, including cellulose, nanocellulose, different lignins. So why should we focus on bioethanol? So also we have to think about it. Okay, maybe we can talk about this other day. And then another what I would like to discuss with you is market aspect. Let's consider market. And this is like simplified view presented by Hydra. So just schematic that we have to keep in mind that for lignin, like for most chemicals, we have curve. And here is market size. And this is like product value. So usually the bigger market size, low product value here, and vice versa. So, okay, if you go to very expensive, very valuable specialties, then usually market size is very low. And very recently, we just submit our review. We consider this in more detail, just different. So here we plot potential lignin production, and we talk about different type of lignin: organosulf, lignosulfonate, craft lignin, and biorefinery lignin here. And also we consider requirement of lignin for different specific application of lignin. And here we not plot price of this product which we trying to get, but we plot what revenue can we get from lignin. What is the difference? Because when we consider revenue, we consider product yield. And for example, vanillin, it's very valuable chemicals. It costs maybe about 10,000 per ton, not 1,000, but why we plot here at about 1,000 revenue, because yield of vanillin may be about 10% from lignin. And then we can get much less revenue from ton of lignin. So what this plot shows us? Again, we have to say that all values are very approximate. Why? Because we don't have a lignin market well established yet. We still don't know a lot of things. So this is just to show some tendency. And okay, last week, Armando Rojas told you most of applications which on this area. They are very high value, but very low market size. And depends on scenario where you work, either your customer or lignin producer. So let's talk about lignin producer here. So if you produce this amount of craft lignin, and we target this application, so we can sell maybe much less than 1% of our lignin for very high price. But what we can do with the rest? And from other side also, okay, if you target, okay, this is very high volume, but value is not so high. So if we use our craft lignin here, then again, maybe it's not the best scenario. It's like, because our goal, our business goal to get maximum amount of money from lignin what we produce. And it was very interesting concept introduced by FPI. They call sweet spot. And for lignin producers, this is sweet spot. So, okay, we produce this amount of lignin, we want to get maximum value. So we go up, and what we can see, this application of our importance. But for example, if you work in bio medical application, you are lignin customer, so you're working on this area. And then, of course, let's say you can use any type of lignin. Basically, you will try to choose what lignin will work the best for your application. So you see, different scenario depends on what type of business you are doing. So now let's go to lignin engineering. And again, message. This slide is from our public data from Ligno Innovate. Now it's part of Suzanne. So this is not secret because it was presented publicly, not all data, because here we just show like relative performance without showing number. So we try different softwood, the same species, let's say pine or spruce or whatever. Organosulf lignin, but they were produced under different process conditions. And then we use this lignin in wood adhesive, and we measure adhesive performance. Obviously, the higher number here, the better. And we compare this with industrial standard, because if you want to use lignin, we have to meet this industrial standard requirement. And we can see that from 30 different lignin, only one fit requirement of industrial standard. 4 in yellow were close, and the rest were pretty far away. So what is the message from this slide? So if you just take random lignin from here, so possibility of success, well, I would say here will be maybe a couple of %. So very likely you fail and say, okay, lignin doesn't work, but it can work if you choose correct lignin. So message, lignin engineering is required. How can we engineer lignin? What variables do we have? Well, we have different type of feedstock. Then we have different type of process. Rough sulfide, which are commercial right now, and the different immersion biorefinery like organosolve, acid hydrolysis, steam explosion, hydrothermal treatment, supercritical water hydrolysis, and so far. Then we can play with process condition, if you can afford it. And then when we already finish our process, we have lignin, we still can have post-process, like lignin fractionation, like chemical modification, particle production. And well, we can use either lignin as is or after post-processing, so we can have different set of lignin. We study their structure, we study their properties, and then we try this lignin for different type of application. And then we build correlation between process type and lignin structure and properties, and then between lignin structure and properties and lignin application. And you can see that this is very challenging because, okay, from one hand, it gives us a lot of opportunity because we have a lot of flexibility. But then it's very challenging how we can understand which lignin is better, which is worse. We have to have very efficient analytical methodology to approach it. And that is why I say, well, large number of lignin required efficient analytical methodology. And to be successful, Rwanda already mentioned about use of artificial intelligence. So we try to do all this lignin engineering through artificial intelligence. We have like a project right now running in our group in cooperation with AI group at Aalto University, very good expert. And we hope to show you results soon, but so far we just show you approach. So for us, it's important to understand all this correlation. We have to understand lignin structure. And well, there is no one single universal method which can define the whole lignin structure because lignin is way too complex. And this is general set of methods what we can use for lignin analysis. It could be wet chemistry, it could be different spectroscopic and spectrometric technique. And talking about wet chemistry methods, okay, it is a functional group analysis. It could be specific degradation method to understand specific lignin features. So, okay, what is pro and cons of this? So usually these methods are dedicated. It means they're very accurate. This is very good. But usually one method gives us one number, or sometimes couple of them. So again, if we talk about the whole lignin structure, what we call lignin elephant, we have to use like quite a few different analytical methods to get comprehensive lignin structure. This is not very productive. So these are good for specific purposes, okay, but maybe not great for comprehensive vision. Another advantage, because then we can use lignin cellulosic without lignin isolation. And this is also advantage of the chemistry method. For spectroscopic, again, we mentioned quite a few different methods, type of method, and the general advantage because they're not destructive first, and then they show the whole lignin, not only specific functionality. And from this, our main focus is nuclear magnetic resonance, NMR, and specifically 2D and carbon. So you can see now NMR spectroscopy advanced quite a lot. So just some picture to impress you. And by the way, this picture already maybe more than 10 years old. So now we are even further ahead. So very briefly, because we don't have time, but you have slides and you can go through them later on. So I just very briefly go through main analytical method in NMR method in Lignin analysis. Okay, it could be proton NMR, so you can see you can get some structure pretty fast, pretty similar with phosphorus NMR. Again, we can get 4 or 5 type of OH group, and please read what kind of precaution we have to be aware for this. But we remember that the lignin structure is very complex, and with a couple of parameters, we cannot describe the whole lignin structure. We do need some advanced method. And then we try to get methods which give us much more information than phosphorus and proton NMR. And one of good example is quantitative carbon. And we work quite a lot to get as much information as possible from quantitative carbon NMR, and published this a couple of years ago. And this is just a list what carbon NMR allow us to do. So you can see that it's quite a lot of information we can get about lignin. And then another very comprehensive method, it's 2D NMR, and specifically SHPC method. So you see usually how it looks like. In reality, this is 3-dimensional, but we usually make this projection at a certain level, and then we have this moieties, and we can see that with 2D NMR we can separate lignin signal much better than we can do in 1 dimension, and give us specific advantages. So how we can get advantage of this high resolution 2D NMR approach? So if you take any technical lignin, either organosulfide cell or Kraft, with 900 very advanced NMR machine with cryoprobe, we can get maybe more than 300 different signals. But problem is that, so what we can do with it? Very simple, we can compare 2 different types. And here we just overlay outside lignin, which is blue, versus other type of hardwood lignin Kraft, which is red. And here we can see, like with this color, what signal are typical for one lignin, but not typical for another. And then we can focus not on the whole 300 signal, but on signal where we have difference, signal which are important. And then what we call profiling or fingerprinting. So then we can focus only on the signal of difference, which may be like maybe around 10, not 300. Then our approach will be much more productive. If we try to get number from 2D NMR, we can see that when we characterize native lignin, we can get total maybe 70–80% with 5 to 6 major structure. But when we talk about technical lignins, it's already like significantly modified, mainly through degradation of beta-4 unit. Then in total, if we just analyze the same structure, it will be like very little, 5 to 15% of total lignin in mole meaning. Okay, then we and other people try some advanced characterization. So we identified and then quantified a structure which formed during Kraft pulping, for example, or other technical process. Okay, we can get more, but again, it's 5 to 20. So let's say this plus this, we are talking about characterization, maybe like 1/4, 1/3 of technical lignin. And summarizing here, so, okay, we have a few hundred signals, but most of them of very low intensity. So this is nature of technical lignin. It's very high variety of signal, but very few of them are above 2 or 5%. And native lignin moieties contribute only a small amount of technical lignin, 5 to 15%. With advanced, we can get a little bit more, but still not everything. So basically, 2D NMR is great for lignin fingerprinting, but for quantification, the whole lignin, it's good to combine with C13 NMR, what we showed before. And now I would like to talk a little bit more comparing different methods here, different NMR methods. And again, proton, phosphorus, carbon 2D. So you see, these are expressed, quite easy to do. But what kind of information we get? Well, 5 to 10 signal, maybe not even the major one. Okay, if you go to comprehensive method, we can get much more information. Again, we can get question how we can use it. Okay, it take more time, more experience, but then we have excellent fingerprinting. We have pretty good information about molecular structure. very comprehensive information about functional group analysis. Then you see, we have to keep in mind, like, this story about Crane and Fox. So we have to use correct method. For example, if we want to determine amount of phenolic OH, in this case, simple and fast phosphorus or polynomal will be much more appropriate than very advanced studio-NMR method, because it does not give you any information about functional group. But from other hand, if you want to use maximum information about lignin, if you want to have lignin fingerprint, we better use comprehensive method. So this is important to understand and use correctly. Then we have to talk about productivity of analytical methodology. And this is also a business case, because this picture from, again, Ligno Innovate. So when we have what we call fingerprinting of lignin, we have a lot of different lignin samples produced under different process conditions from different biomass, and we have pretty short time. So, and in 6 months, we can get this amount of different value, and you see more than 50% of this information was obtained from NMR approach. And this productive analytical methodology allow Ligno to get first patent on lignin structure, not lignin application, not lignin production, but specific lignin structural characteristic. And this was very big achievement. And now Susanna Innovate still continue working on this. And of course, they have all this database, different characteristics. So they consider this like main asset for business case development of lignin. Also, we can get a process correlation between process and lignin structure through MATLAB. This is not artificial intelligence, simple MATLAB. And also it was patented. But when we talk about other type of correlation between lignin structure and lignin performance, then it's just one simple example. When we work on lignin application, PF adhesive. And it's well-established theory, a lot of people believe on this, that performance of lignin directly proportional to so-called number of reactive centers, which are shown here, which is auto-position to free phenolic OH, and which can be easily measured by phosphorus and Nano. Okay, so we take different set of different lignin, hardwood, softwood, different process, and the measure amount of reactive center we plot here, and then we measure adhesive performance. And what we can see is that we have no correlation whatsoever between number of reactive center and adhesive performance. And in fact, the best lignin has the less amount of reactive center and has a much better performance than all others. So conclusion, we have to be very careful with this educational guess when people say measure just simple amount of OH group and they make very big claim about application performance. And the same story, we did not have any correlation between adhesive performance and molecular mass. This is another theory. So what is important, that other variables can be more important than this, and we have to consider this structure performance correlation much more carefully. Then few words about biorefinery lignin. Unfortunately, there are quite a few dogmas around biorefinery lignin, and one of them that most of them are very high, very low purity, and then people correlate directly like low purity, it means low performance, and correspondingly very low value. Then, okay, we are aware that we can produce high purity lignin from crude biorefinery lignin, but people believe that there is technical and economical challenges for this. And well, some particular conclusions that most of biorefinery lignin are hardwood. For example, you have a lot of eucalyptus in Brazil, and they are much worse for applications than compared to softwood lignin. So all these bring people to believe that biorefinery lignin are low value product. And with our research, we really challenge this dogma. And again, I show just a few results. So again, the same plot, but now we correlate this adhesion performance with lignin purity. So is lignin purity a must? And here we have pulping lignin with very high purity, very low residual sugar, residual carbohydrate. And then we have crude biorefinery lignin with very high amount of residual cellulose, 40%. And again, you see it's completely opposite what we believe, that crude non-purified lignin has the best performance. So we try to explain this. And when we look at literature, there is quite some information on lignin cellulose synergism bar between pure lignin and, let's say, CNC, CNF, or pure cellulose in this application, like carbon fiber, thermoplastic, and vice versa, because sometimes the presence of lignin, small amount of lignin, like up to 10%, improve performance of cellulose, nanocrystal, and nanofiber. And you can see that Aranda Rojas give you a few examples last week. But most of these examples were with high purity CNC or CNF. Here we have like pretty low purity. We are not even sure that these are crystal, but high crystallinity cellulose. So, okay, our effect is not so strong like in this application, but you see, if you talk about production cost of our crude biorefinery lignin is compared to pure CNC, it's 20 times lower. So then it's very attractive for economical point of view to find the application for this. And also what we learned, I don't have time to show, but it's not like present of cellulose. Cellulose component must be optimized for specific characteristics like molecular weight distribution, degree of crystallinity, and so on. And also Aranda shows this slide, and I decided to repeat it because it was quite a few questions when he showed about lignin nanoparticles through his method. And I will not go through this slide. So basically, it was reported by Mariko Ago, this method to produce it, and then Camilo de Assis calculate economical feasibility of this process. And actually, because I'm close on this paper, we conclude that, okay, if you use like alpine lignin, like kraft, lignosulfonate, production cost in this range. But if we use biorefinery lignin, we can drop it even further. So this is a good advantage of biorefinery lignin. Another thing what we found in this process, it's not related to biorefinery lignin, but when we choose correct solvent, we can drop production cost even more. So this is very important because it's of very high interest, this type of lignin intermediate for high value application. And also I have to mention, I don't have this data on my slide, but at our department, Monica Osselberg group worked with another method to produce lignin particles, they call colloidal particles, through solvent shift. And also did quite a lot of economical evaluation, and during last year they improved economical feasibility of their process. So you see, important is not only to show like scientific feasibility or technical feasibility, but also to show economical feasibility of lignin product for successful application. And then I'm already pretty close to my end of my presentation. So I just want to highlight it. We have to rethink specifically biorefinery lignin. We know quite a lot of information about kraft, but biorefinery lignin is kind of new in terms of science. And since we can use either non-purified biorefinery lignin as is for high value application, not for low one, or we can easily get green, technically feasible and cost-efficient way to upgrade lignins through purification, fractionation, derivatization, and also lignin micro and nanoparticles, and we can combine all this process in one pot. So then that's why it makes cost-efficient. Then I have to conclude that biorefinery lignin can and should be used in various high-value applications, not just cheap fuel or cheap feedstock. And finally, I'm coming to end of my presentation. So, final remarks. Yes, lignin is very complex, irregular polymer. And even native lignin is very complex and irregular. But if we're talking about structure of technical lignin, it's getting even much more complex and heterogeneous. So if you use lignin for high value application, this can give the whole renaissance for the whole sugar-based biorefinery. So it can make it economically feasible. How we can do it? We do it through lignin engineering by understanding structure, performance correlation, and correlation, of course, with process condition. And here you see lignin structure is key element on this correlation, and that is why analytical methodology is primary importance. I show only one slide, but I want to highlight that educated guess related to structure and the real performance correlation must be avoided, because quite often it gives us very wrong conclusion, misleading. So we really have to consider experimental evidence when we talk about lignin application performance. And of course, we have to consider economical issue when we consider like industrial lignin valorization. And finally, since this lecture is mostly for students, so I would like to bring, let's say, our wish from old generation to new generation lignin chemistry. So when we talk about lignin structure and the all lignin issue, consider all facts, not just selected, because this is very complex. Remember elephant. So to see the whole elephant, you have to have all information. Don't just select what you like and ignore the rest. Then it's very important, don't be obsessed either with very common theory or dogma, and I give you a few examples, or with big names. You know, all this theory made by people, and everybody, even very genius people, can make a mistake. So be critical, use your own brain, of course, honest, that is, I say, still consider all fact, not whatever you like. And also be very careful with educated guesses. We do need experimental evidence, not just like speculation between very basic characteristics and especially within application. So this is what we have to develop. Like we have to get a lot of experimental proof for our conclusion. So thank you very much for your attention, and I will be very happy to answer any question and discuss. Yeah. Okay, so again, our lignin group, and actually quite a lot of work we did together in cooperation with Boku group. So how usually people say, okay, these are real people who do the work. But okay, I would like to stay on this slide. Okay, please.
Спасибо за лекцию, господин Balakshin. Это было здорово. Was it okay?
Yeah, I hope it's.
Thank you. Thank you very much for the elucidative explanations. And we do have a lot of great questions. And the first one from Maxim Galkin. He says, thank you, excellent presentation. And then the question, how much for the same species do age, watering, and other growing aspects do affect lignin structure? Could be lignin structure be modified through time?
Sorry, could you please repeat the question, because I did not understand exactly. Maybe
sure.
Hearing not good.
He asks about how much the same species do age, watering, and other growing aspects do affect lignin structure for the same species.
Okay. Yeah,
and
very
if
good.
The lignin structure can be modified through time.
Yes, because it's out of speculation, but honestly, I did not see much evidence, because, you know, when we discuss like, okay, how much difference in different lignin, we also have to consider what is experimental error. And in my opinion, quite often when we even discuss like even different softwood species, for example, spruce, pine, fir, difference what we see in literature, in my opinion, they are mostly related to analytical method or maybe interpretation of different analytical data. So far, so let's say to make this conclusion, we really have to compare head to head. So not compare different literature publication, but use the same method, maybe the same hand, and different lignin characteristic. And also, what is critical, we have to understand experimental error, because some methods are very comprehensive, but okay, they have deviation maybe plus minus 5%. So if your difference between your different lignin within 5%, you will not see it. Then you have to choose method which has much higher accuracy.
I have a question about Krebs lignin isolation made by Priscila Moreira from the Federal University of Viçosa. She firstly said, great presentation. And then she asks you to comment a little on the difference in purity obtained by isolations from lignobus and lignoforce processes.
Well, maybe I'm not the best person to address it, because, you know, most of methods are kind of, in most of cases, confidential because they are for company. And by the way, LignaBoost lignin is not a specific lignin. It's LignaBoost is method, but then they use this method for any industrial feedstock and still call it LignaBoost, as much as I know. So it's the original lignin feedstock and from which mill it comes. But in my general opinion, very general, both of them provide pretty high purity in terms of purity, and there is some method to improve if needed. So basically, but you know what is interesting, because I know one patent from LignaForce, and they use non-purified LignaForce lignin in adhesive and found that this show much better performance than purified lignin. So it's again like what I show our slide on biorefinery lignin, where we have carbohydrate. Here was a lot of different inorganic impurities. But lignin lignin perform much better. So I would say that both method, both group has way to improve purity if they need. Well, I would say it's in terms of purity, they're, in my opinion, pretty comparative. There's some small difference in other, like for example, volatile component, maybe like filtration rate and so on. But in terms of purity, both of them pretty high purity.
Now another question about biorefinery from Kalel Dias Pereira, also from the Federal University of Viçosa. He asks, what techniques besides fractionation can be performed to mitigate the effects of lignin polydispersity in biorefinery?
Well, this is not only for biorefinery. By the way, I have to comment, because when we say biorefinery, it has quite different meaning, at least in North America and in Europe. I don't know about Brazil. Because in North America, people talk about biorefineries, they mean sugar-based biorefinery, not pulp. In Europe, when they say biorefinery, people definitely include pulp and lignin, like kraft, lignosulfonate, and I think this is correct. So we have to define what we mean under biorefinery. So, okay, if you talk about sugar-based biorefinery, yes, but I would say in this case, it's common for sugar-based biorefinery and for maybe for kraft lignin. I would say two major approaches. Either solvent fractionation, when you use different solvent mixture, specific concentration, you get different polydispersity, different molecular weight, different purity. And another way, it's ultrafiltration through membrane. And by the way, it's like small company in Finland called MedGen. So they also have kind of fractionated lignin, but at the same time, they oxidize it with commercial lactase. So they claim they fractionate and fractionate very efficiently. But it's not only fractionation, but it's also modification of lignin during fractionation. So these two methods are.
But don't they have problems of pressure when using ultrafiltration? Isn't it hard to do?
Well, it's I don't know current state of the art, because before, yes, membration of, well, each method, I don't know which method is better. We have to really calculate economic, and of course, each group push for their own method. So I'm not sure we have all information available to judge like publicly. So we really have to compare like real achievement in ultrafiltration and in solvent fractionation. Yeah, membrane clogging and then pressure raise. So membrane life, it's very important. So filtration unit is critical, but as much as I heard that people who work on this membrane technology, they improve a lot. So I don't know if it's commercially ready, but definitely it's very great progress in this area. And also for solvent, because, okay, before people suggest some kind of exotic solvent, maybe not green and not environmentally friendly. Now, VTT and other people, well, including even our approach for biorefinery lignin, we use what we call kind of green solvent, for example, ethanol or aqueous acetone. So then are much more feasible and not so harmful for industry, for environment. So both approach has chance, but which will work, we have to see. Basically, industry will tell us, because again, everything will be up to cost and performance. So everything comes to economics.
The next question came from Marcelo Muguet. He works in Klabin company. And he actually has aged yesterday. So first of all, happy birthday, Marcelo. And then the question, is there any analytical tool that measures the total amount of reactive groups and also the accessibility of these groups? Could accessibility play a role on, for example, adhesives performance?
Well, again, I showed some slides when it was pretty straightforward, like people easily measure what they call reactive center through phosphorus NMR. And have, I would say it's not was even hypothesis, it's considered like a dogma that, okay, more reactive center, more reactive. But what we show is not always the case. Sometimes it works, sometimes not. Talking about reactive center in general, we have to define because for different application, reactive centers, they will be different. If we have phenolic resin, it will be like maybe aromatic ring. If you talk about polyurethane, it could be aliphatic OH. But nothing what we must keep in mind, because quite often people correlate lignin performance with lignin reactivity, chemical reactivity. And what often missed is a kind of compatibility, miscibility issue, which we addressed quite a few presentations and publications by Professor Glasser, who is very famous application lignin expert. So he shows that miscibility, compatibility issue is very important, and sometimes I think they might be even more important than reactivity issue. And maybe like if you remember our slide when I show, okay, it's no correlation with reactive center, but then probably what really play a role is exactly this compatibility issue. And when adding different components like cellulose change application much more, so it's nothing related with reactivity. It's something with miscibility.
Now we have two questions about the use of lignin and also about the feasibility of some usages. The first from Kyle Mikhail, he says, congratulations for your presentation. And then he asks if you think it's feasible to use lignin from primary sludge.
From which sludge? Sorry.
The primary sludge. From the
primary sludge, it's like on paper mill, right?
From treatment.
Well, I mean, in general, yes, I think it's possible, but I cannot give like any specific recommendation. We have to take a look, and depends on application. Well, what we have to, well, we have to look for some kind of waste stream, because if we just use pure nice wood, then it can result in deforestation. So it's also dangerous. So we have to consider stream which are waste, so this improve ecology, and then it will be our feedstock. Yeah, if we have lignin, then let's try to consider. But honestly, I don't have any experience. It's just my like very generic opinion.
Still going through this path, a question from Amanda Carvalho from the Federal University of Viçosa. He asks, do you think it's possible to produce aviation biofuel from black liquor?
Again, I am not expert in everything. Actually, I am more lignin chemist than lignin application expert. Yeah, of course, a lot of people do it, try, and some people claim that they can do. At least I know, even let's say we have even joint publication with one group from Spain. They use supercritical water hydrolysis to depolymerize lignin, including black liquor. And then in reality, they can come to monomeric and oligomeric fraction. And then they claim that this product can be used in aviation fuel. But again, what is my strong point? It's kind of educated guess. We have to show, we have to take this product and show that it can be used. And of course, it's not the only. Some people try. I think it's a very good idea to use black liquor directly, because then you don't need spend money to isolate lignin, wash it, purify it. So if your process allows this, so it will be great. But honestly, maybe I overlook something, but so far I didn't see like, I would say there is potential, but I don't see like final conclusion that, okay, this lignin is used in aviation. Maybe I overlook something, but this is as much as I know.
Now a question from Professor Angélica de Cássia Carneiro from the Federal University of Viçosa. She congratulates you for the lecture and asks, What are the most promising main techniques for increasing the reactivity of craft lignin?
Again, reactivity where? Because you see, depends on application. Reactivity is like, it's very generic term. So we have to talk about, well, for example, if people talk about phenolic adhesive, so they try to increase reactivity in aromatic ring. And the VTT has a couple of approaches they call cut lignin, when they have this quite simple process to increase, to produce more available ortho position in lignin. And by the way, because when I thought, okay, it's no correlation in our specific case.
Yeah, I'm pretty sure that for adhesives application is the one that she's most interested in.
Yeah. Adhesive, yes. So then probably it kind of, it could be modification aromatic ring. Another common type of improving reactivity for lignin in adhesive, it's phenolation. So you can just take like monomeric phenol and kind of modified lignin, get phenolated lignin, partially phenolated, and then use it directly to adhesive or to formulate PF resin. But for example, if you talk about polyurethane and thermoplastic, then for example, oxypropylation, it's quite common. So you see a completely different reaction. So it's important when we talk about lignin reactivity, we must define reactivity where. Or another case, for example, reactivity in lignin degradation. So then we have to increase, for example, number of beta 4 and decrease number of condensed phenolics. So it's very process dependent. Reactivity, what I mean.
Yeah,
so
and she actually also asked about the range of thermal degradation for soluble lignin.
Thermodegradation for which lignin?
The soluble one.
Sorry, but what do you mean soluble?
Sorry?
You mentioned, you say soluble lignin.
Yeah,
Soluble.
probably acid soluble lignin, I guess.
Acid soluble lignin in probably some biorefinery process. Well, okay. First, honestly, nobody knows what exactly is acid soluble lignin because there are a lot of discussion. If you talk about acid soluble lignin in biomass. And yeah, we have quite a lot of acids, well, like reported like acid soluble lignin, especially in hardwood, like eucalyptus and other species. But nobody can report their structure, and some people even think that this is not real lignin, it should be some kind of artifact. But yes, okay, acid soluble lignin, of course, when we talk about biorefinery process, like after hydrolysis, of course, this acid soluble lignin will be first to dissolve, and very likely it will be low molecular weight because it's soluble, and very likely it will be hydrophobic. So first, a challenge to recover it from process stream. So some processes are suggested like resin, and then of course, I think it's my very general opinion. I didn't work on this, but since it's low molecular weight, hydrophobic, water soluble, so in certain application where we need really water soluble lignin, which is not always a case, it could be used, for example, surfactant, like surface active agent or reagent, and maybe also for production of low molecular weight lignin oligomers and monomers. And again, what we talk about fuel application, like biodiesel, something like this. Again, this is like very generic. Don't take it like very serious. It's just like speculation.
Now the last question, which came from Marcela Cura, also from the Federal University of Viçosa. He's from inside the Pulp and Paper Laboratory. She says, thanks for the lecture, and asks, are there any studies for the use in biorefineries of lignin extracted from grasses? And she also asks if the lignin 8 is really a problem.
Again, just to make sure, from biorefinery lignin from grasses?
Yes, like sugarcane.
Okay. And
this is about the para-hydroxyphenyl lignin, if it's really a problem for the process.
Okay. No, well, I would say most of information, most of biorefinery process, they deal with hardwood. Of course, non-wood lignin like grasses, bagasse, and so on. They also work in biorefinery, work quite well. And in Brazil, you know, because you have quite a lot of experience with bagasse, and I think you are a leader in this range, in these terms, like compared to even United States and Canada. Okay, to produce bioethanol or biosugar from bagasse lignin, I have not seen much. And well, again, definitely we have to consider structure of lignin, because what determines structure of technical lignin is two things. Of course, process, what we use, but also starting feedstock biomass. And of course, non-wood lignin, grass lignin, bagasse lignin structure is quite different from softwood or hardwood. So we have to keep it in mind, and this will result in structure of final technical lignin, like biorefinery lignin. Well, honestly, I do have experience, like personal experience, both in organosolve process and in supercritical water process, Renmatics one, when we work on this company, because we work with non-wood lignin, but unfortunately all this information is company confidential, so I cannot talk about this right now. And publicly, I don't see much. Well, we can consider what we consider biorefinery, because in France, there is a company called SIMV, SIMV, which use organosolve pulping through formic and acetic acid specifically for grass lignin. So they have some information. I would say some information, maybe kind of structure, about structure, I would not agree. It's again method dependent, some quite good. Of course, they try a lot of application, but they still at the kind of pilot scale. They try to commercialize, but cannot do it so far. About bagasse, I don't see public information. Maybe so. You guys from Brazil, you have to work on this report. Company have definitely, not only one company has it, but this is not public. And what I know, I cannot comment on this.
Sure. I guess it's all we have, Mr. Balakshin. So once again, thank you for your attention, your kindness. It's been a pleasure to hear your lecture. Hope to have you again with us. Yes, thank you very much. It was a very interesting experience for me, because it's the first time when I present online and even getting records. So, but I'm very glad that you have some interest and quite a lot of questions. So thank you for your invitation, and all the best for you all, for Visoza and for all participants. Muito obrigado. Спасибо. Unfortunately, our first edition of the International Virtual Seminar on Wood Pulp and Biorefinery is coming to an end. I hope you all have taken the opportunity to acquire a lot of knowledge during these 5 days of lectures. Once again, thanks to the speakers, the registrants, all collaborators of the event. Have a great week and stay safe. See you in the next opportunity. Bye-bye. Bye-bye.